Here, let's discuss one famous machine learning classification technique called Naive Bayes Classifier. So, this is a probabilistic approach. So, consider we have the dataset D, where for any input feature X, output is Y, which is 1 or minus 1. So, basically we are talking about binary classification here, where we have two different categories. So, Naive Bayes classifier can be extended for multi-class classification as well. But here primarily we are starting with binary classification. Consider we have this dummy data set here. We are given the glucose level and the class whether it is normal or high risk. And also we have plotted this here. This is a dummy plot where we can see that risk is increasing with glucose level. And this, consider this normal is 1, high risk is minus 1. So that's how we are categorizing our output class. Now consider any input X and any output Y is coming from two random variable X, capital X and capital Y. So for any new data, we need to calculate probability of this Y equals to Y, capital Y equals to Y given capital X equals to X, which is what probability of output given input. So this we can, for simplicity, we can write it as probability of small y given x, small x. This we need to calculate, but from the training data set we already have the prior probabilities, like probability of x, capital X equals to x given capital Y equals to Y, which is, for simplicity we are writing as probability of x given y, and this is probability of y. Now this is actually probability of input given output class, and the second one here, this is probability of the output class, right? So this too we can calculate from our training data set as well. So for any output class we know the input, right? So this probability we can calculate. Or also with probability of any particular output class, that also we can calculate from our training data set. So we have to calculate this one for our using our Naive Bayes classifier. Now let's see this Venn diagram first to understand few things. So this is the X, let's say, and this is Y. That means X intersection Y is this part. This is Y given X. So given we are having X, so this is X, right? So given we are having X, what is the probability of Y? So that is Y given X. Now this is Y, right? So given we are having Y, what is the probability of X? So that is X given Y. Now if X is input, Y is leveled output class for our data set, we will know probability of X given Y, right? For any given class, probability of input, for probability of X given Y. We have to calculate for any new input what is the probability of the output class. So that is probability of, also we can write is Y equals to Y, X equals to X. So this is probability of, for any input, what is the probability of output class. Let's see few calculations simply. So probability of X times probability of Y given X is equals to probability of X intersection Y. How it happens? Probability of X, and given that X happened, what is the probability of Y given X? If we multiply this two, we get probability of X intersection Y. From here you see probability of Y times probability of X given Y. This is probability of X intersection Y. So that means this one equals to this one, right? So probability of X times probability of Y given X equals to probability of Y times probability of X given Y. we have to calculate this thing, right? Probability of y given x, probability of output class given any input. So this we can calculate by dividing this one by this probability of x. So that's how we are getting this equation. Probability of y given x equals to probability of y times probability of x divided x given y divided by probability of x. Now, probability of y, this is the probability of the output class from the training dataset. This is prior probability of the output class. Probability of x given y, this is the likelihood. Probability of input given the output class, this is called the likelihood. And probability of y given x, like probability of output given any new input. So this is the posterior probability we will be calculating. And this equation is called Bayes theorem. Our Naive Bayes classifier is based on this Bayes theorem. Now, few quick thing here. You see this probability of x. This is fixed for a training data set, right? So we'll see how. But you see that means probability of y given x will be proportional to this numerator part. Probability of x given y times probability of y. Now, quickly expand this probability of x to understand it better. So, probability of x can be written as probability of x intersection y union y complement. So, let's see here. So, let's say this is universal set, right? And this is y. So, this is y complement, right? So, y union y complement, that means the whole universal set. So this is the universal set here. Now what we are calculating here is probability of x intersection universal set. And what is that? If this is the universal set and this is, let's say, x, so intersection of x and universal set is the x only. So this holds, this thing what we have done here, this is correct. Now let's expand it further. So if we expand this, we get probability of x intersection y union probability of x intersection y complement. This is fine. So this can also be written as probability of x intersection y plus probability of x intersection y complement. And this probability of x intersection y is what? Probability of x given y times probability of y. That's what we got from here. Probability of x intersection y can be written by this or this. So that's how we are just expanding. Probability of x intersection y is probability of x given y times probability of y. And probability of x intersection y complement is probability of x given y complement times probability of y complement. So this is the whole probability of x, right? So given for there are two types of output, one is y complement, let's say here. So for these two types of output, what is the probability of input? So that if we sum them up, then basically that is probability of x. So this I expanded just to have the clear vision about this computation. Now for the new data, of course, we have to calculate this probability of y given x, right? And from the training set, we are getting this prior probabilities, probability of x given y and probability of y. Now there are two class. We will calculate probability of 1 given x, probability of output class 1 given input x, and probability of output class -1 given x. These two probabilities will be calculating, and whichever will be higher, that will be our output class. If this probability is higher, then the output class is 1. If this probability is higher, then output class is -1. Now how we will calculate that? From the Bayes theorem. It will be probability of x given 1 times probability of output 1 divided by this whole thing. This is basically probability of x, right? So this part is basically probability of x equals to x. Just we have expanded. Probability of x given y equals to 1 times probability of y equals to 1 plus probability of x equals to x given y equals to minus 1 times probability of y equals to minus 1. And for this probability, we'll get probability of x equals to x given y equals to minus 1 times probability of y equals to minus 1 divided by the whole thing. This thing and this thing is same. The denominator is same. Probability of x, input x given output 1 times probability of output 1 plus probability of input x given output minus 1 times probability of output minus 1. So you see, we saw that this 2 denominator part doesn't change here, right? So this 2 is basically probability of x given x. So that's how we calculated this 2, and you see we also saw this one is proportional to this numerator and this one is proportional to this numerator because this denominator doesn't change. Whatever, now we got these two probabilities, right? So whichever probabilities will be higher, that will be our output class. So output y star, this will be the argmax of y from these two probabilities for different probabilities. So this is for output class 1. This is for probability of output class minus 1. And we'll take the argmax. If we are talking about multi-class classification, then for each of the output class, instead of 1 and minus 1 for multi-class classification, we can have different classes like 0, 1, 2, 0, 1, 2, 3, 4 and all different classes will have, and for each output class we'll calculate such probabilities, and then whichever probability will be higher, we'll take that class. Now consider we have multiple input features. Earlier we only saw that glucose level was the input and class was normal or high risk. Now consider we have multiple input features, glucose level, age, BMI, and the output is normal or high risk. Normal is 1 and high risk is minus 1, let's say. Now it will be the similar thing what we did earlier. So we are considering this input features is coming, input feature x is basically d-dimensional and output is 1 and minus 1, and this x and y inputs and outputs are coming from random variables x and y. So for new data, we have to calculate probability of output class y given input is this x1 to xd, the d inputs. For the D inputs, D inputs, we have to calculate the probability of output. Using the Bayes theorem, it will be same. Probability of input, this x1 to xt, given probability of output class y times probability of output class y divided by probability of input x1 to xt. Now one thing here is Naive Bayes considers the features, this x1, x2 till xt, these are independent. So here what it is saying is this glucose, age, BMI, these are not related. So but that is not always true, right? So age, BMI, glucose, this might be related somehow, but Naive Bayes classifier considers these are independent. So as they are independent, so we can expand this probabilities or these probabilities. So probability of input class x1 till xt given probability of output class y can be written as probability of x1 given probability of output class y times probability of input x2 given output y times till probability of input xt given output class y. Then we are multiplying this output probability of output class y divided by this one. Probability of input x1 till xt can be written as probability of x1 times probability of x2 till probability of xt. And this way we are writing, because naive Bayes considers this input features x1, x2 till xd are independent. So this is how we can expand for independent features. Now this is we are calculating. So this can be written as, okay, this is the probability of output y given all the inputs x1 till xt, and this will be proportional to this numerator part, which is probability of input y. I wrote it first, then this product of all the terms from I equals to 1 to d, probability of input xi given output class y. And this is for output class y, this is the probability. So we can have multiple classes, and for each output class we'll calculate this probability, and then from that we'll take the output class that is having the maximum probability. So output y star will be the argmax y of this probability. So now let's quickly see one example here. So consider we have this data set. We have weather, temperature, and whether someone is playing or not playing that day. So we have weather like sunny, cloudy, rainy, like that. Temperature can be hot, mild, cool, etc. And this is the output class, no or yes. Let's say yes is 1, no is -1. Now we have to calculate probability of playing given the weather is sunny and mild. So this is basically probability of playing is the output class given there are two features x1 and x2, right? So this we have to calculate, but from the data set we can calculate this prior probabilities. So probability of playing given sunny and mild can be written as this using Bayes theorem. Probability of sunny mild given playing times probability of playing divided by probability of sunny and mild. Now see, probability of playing we can calculate from here, right? So we have in the data set we can see that how many times this person is playing or not playing. So probability of playing we can calculate here from here. Probability of sunny and mild both, that also we can calculate from this data set, where all we had weather sunny and temperature mild. Now this one, probability of sunny mild given probability of playing, how we will calculate that? So naive Bayes will consider these features are not dependent, right? So this part we can expand. Probability of sunny mild given playing can be expanded as probability of sunny given playing times probability of mild given playing. And probability of sunny mild basically is what? Probability of sunny from this weather times probability of mild. Right? So this all these probabilities we can calculate from the given data set only, right? After we calculate that, we can easily calculate this output probability. So probability of playing given sunny and mild, that will calculate, and what is the other class? Probability of not playing. So we'll again calculate probability of not playing given sunny and mild. Right? So this too will calculate. So whichever probability will be higher, if probability of playing is higher, then our decision will be output class playing. If probability of not playing is higher, our output class will be not playing. In later videos, we'll see this Naive Bayes classifier can be used for many other applications like spam classification, text classifications, and all this.